Hello there guys and welcome back to another epic inexorable maths video. In this video we're taking a look at implicit differentiation, okay, for the first time. Now we are today going to look at what implicit differentiation actually is, why you'd use it, and where does it come from, because it's quite strange. It's quite a strange one to actually think about. So let's do an example. What is implicit differentiation? First of all, let's talk about that. So we use this word implicit. It just means when y is not given explicitly. So an explicit situation would be a y equals f of x. How do we differentiate that? Well, we simply do dy dx on the left hand side, and we differentiate whatever the right hand side tends to be. So, you know, f of x could be x squared, and we would get the dy dx equals 2x. It could be x cubed and we get 3x squared. In general, it would just be the derivative of f of x. Just like that. That's all it means, that's all it is. We differentiate the left hand side and we differentiate the right hand side. You always differentiate the left and the right hand side of an equation when you do differentiation. You just might not notice it, but notice how in this case we are differentiating the left and the right hand side in order to get the sort of expression in terms of the derivatives. Awesome, I'll leave that there. So, what's an explicit example? Well, a very popular and common one would be something like the equation of a circle. So maybe x squared plus y squared equals r squared, right? Where r is the radius of that circle, okay? If I said to you, okay, find the derivative of this, you might say, how do I do that? Or you might say, oh no, that's fine. We'll just make y the subject. So we'll take x squared away from both sides. We'll get y squared equals r squared minus x squared, and then we'll take the square root of both sides and we'll get y equals plus or minus the square root of r squared minus x squared. Boom. And then we differentiate that. And you can differentiate that, but you'd have to consider it as the positive and the negative root. So you'd have kind of two different expressions for the derivative depending upon your y value or your x value, and that's not very convenient. Also, it's actually not the easiest thing in the world to differentiate. You know, it's definitely doable. You can do a u substitution. It's fine. You can do it. But it's not actually that easy. And it creates all these problems with that plus or minus. You don't really want to do that. So there is another way. There is a way that is easier. And this way, by the way, implicit differentiation, I'll also mention, is one way, probably the easiest way, to derive the product rule. And the product rule derives the quotient rule. So really this is the basis of all of those different rules for differentiation. This unlocks so many different derivatives. So it's really important. So how do we do it? Well, this is how implicit differentiation actually works. What you do is if you see any functions of x, so this is a function of x, for example, x squared, you differentiate them like normal. So the derivative of x squared is 2x. Amazing. And then if you see any functions of y, this is something that you won't have encountered before, because normally the only function of y that you get is just y. It's y equals f of x, right? But now you have a y squared, or maybe a y cubed, or maybe a sine y, or a cos y, or a tan y, or an e to the y, anything like that. What you do is you almost pretend that the y is an x, and you differentiate it with respect to y as though it were an x. So for example, the derivative of y squared with respect to y is 2y. Okay, so we differentiate with almost as though it's an x. So, you know, if that was an x squared there, the derivative would be 2x, right? It's a y squared, so it's 2y, if that makes sense. But there's one thing that you need to do when you differentiate any function of y. You only do this to the functions of y. Every single function of y you have to do this to. You times it at the end by dy dx. And we will talk later in this video about why you do that. But this is just an example for now. And you have to differentiate, as I said earlier, both sides of the equation, the left and the right. Right now, r squared is a constant. It's a number. It might be the number 9 or the number root 3 or anything. It could be anything, but it's a constant. It's not a function of x or y, which means the derivative of r squared is always going to be 0 because r squared is a constant. It's not a function of x or y. It's like differentiating the number 5. That's what r squared is. It's like the number 5 or the number 2 or anything like that. So the derivative is 0 essentially. Awesome. So now we have this expression. Now what we do is we simply make dy dx the subject, and then we'll be done. So let's take 2x away from both sides. We get 2y times dy dx is equal to negative 2x. Then let's divide both sides by 2. So we get y dy dx equals minus x, just dividing both sides by 2. And finally, divide both sides by y. We get dy dx equals negative x over y. What this is saying is that the derivative of the equation of a circle, because this is the equation of x squared plus y squared equals r squared is the equation of a circle, it's saying that the derivative of the equation of a circle, as long as it's at the origin, is just the negative of the x coordinate divided by the y coordinate. What this is saying is the derivative not only depends on the x coordinate, which it normally does only depend on the x coordinate, like x squared for example, it only depends on the x coordinate, but actually the derivative of the equation of a circle also depends on the y coordinate as well. And the reason for that is because, if you think about a circle, and it's kind of on an axis like this, well, you've got some x coordinate. Let's say that, this is your x coordinate here that corresponds to that point there. But hold on, there's also a point below. So there's 2 different y coordinates for every x coordinate, or almost every x coordinate, which means that we do have a situation where you also need to specify which y coordinate you're looking at. That's why you need the x and the y in order to, give the steepness of the curve at a tangent, because it's going to be different at those 2 points, if that makes any sense. Don't worry too much about that though. We don't really need to be looking at that, but that's an explanation as to why the derivative of a circle is like this. So I did something a little bit suspect earlier, right? Because that's how we use implicit differentiation. You take any function of y, essentially, you differentiate it as though it was a function of x almost. So y squared goes to 2y, sine y would go to cos y, etc. And you just multiply every term that's got a y in it, by dy dx. And then you make dy dx the subject and you're finished. Boom, done. But why are you allowed to do that? Why are you allowed, first of all, to just times it by dy dx like we've done here? Where does the dy dx come from? Why don't we do it for x, etc.? Where is this coming from? Second of all, why are you allowed to differentiate y like this? Why are you allowed to actually do that? Because y squared differentiates to 2y with respect to y, sure, but we're differentiating with respect to x. So why are you allowed to do that? All will be revealed right now. So this is where this whole thing actually comes from. Where does implicit differentiation actually come from? This is where it comes from. What our goal is here is we want to differentiate, so d dx, not y, we don't want dy dx, we just want to differentiate a function of y. So f of y. We want to find the derivative with respect to x of a function of y. So we want to see what the derivative of, let's say, y cubed is, or tan of y squared, or something like that. Anything that you want, any function of x that you can think of, replace the x with a y, and that's your function of y. We want to differentiate that in general, see what that does. So what we do is we use the chain rule. The chain rule is what enables us to use implicit differentiation. So the chain rule says, well, if you're having trouble differentiating something, make a little u substitution. We've got a video on the chain rule if you want to check it out. But what we're going to do is we're going to say let u equal our function of y, right? Okay, now we're just going to go ahead and we're going to do du dy. We're just going to see what happens when you take the derivative of u with respect to y. What happens then? Well, if we do du dy, remember we're differentiating with respect to y this time, not x, y. Well, what we end up getting is f prime of y, right? The du dy is simply the derivative of y. Of course it is, right? If f of y was y squared, then du dy would be 2y, right? The derivative of y. Hope that makes sense. It's the same as with the chain rule. We're just using y's instead of x's. But what we are actually looking for is du dy. That is actually what we want. This time, we don't want dy dx. That's how the chain rule normally works. And so the difference between this situation and a normal chain rule situation is that instead of looking for dy dx, which is what we're normally looking for with the chain rule, we're looking for a du dx. The reason why we're looking for du dx is because du dx is this dx f of y. That's what we're actually trying to find. We want to see what the derivative of a function of y is with respect to x. That's what we're looking for. So we want du dx. That's actually what we want. So we need to see how we can make du dx. Well, we've got here our du dy. We've already got that. We've worked it out. It's f prime of y. It's the derivative of the function of y with respect to y. It's fine. So how do we make du dx? That's what we want, du dx, when we've got du dy. What can we times du dy by in order to make du dx? Well, we can times it by dy dx. Think about this, because the dy's cancel out, don't they? Boom, they're gone. Du dx equals du dx. Seems legit to me, seems to be fine. Du dx equals du dx, right? Because the dy's cancel out. So I hope that you agree, I agree as well, that du dx is du dy times dy dx. Awesome. So what that means is du dx is equal to du dy, which is f prime of y, multiplied by dy dx. Awesome. And so remember what we said that du dx was. We said, or rather what we said u was, we said that u was f prime of y, which means that the derivative, or f of y, sorry, the derivative of f of y is the derivative with respect to y of f of y multiplied by dy dx. That is the idea behind implicit differentiation. What this is saying is, if you want to differentiate a function of y with respect to x, so like our circle example, all you do is you differentiate it as though it was a function of x. You actually just differentiate your y, your function with respect to y. That's the f prime of y part. And the second part is multiplying by dy dx. You are timesing by dy dx afterwards. You have to do that to every single individual term. That is how implicit differentiation works. Okay, so in the future we'll do lots and lots of videos on implicit differentiation. It's quite a big topic, and it allows us to prove, as I already said, the product rule, the quotient rule, etc., etc. It's really useful. If you enjoyed this video, thank you so much for watching. Like, subscribe, share with your friends and family, and I'll see you in the next video. Cheers.